Every time you log into a website or search a catalog, your text input travels from your browser to a back-end server. It is easy to assume that a database breach means the database engine itself was compromised. But SQL injection is an architectural failure of the web application, not the database. The vulnerability occurs when a web application takes raw, unsanitized text from a user and drops it into the execution engine of that back-end database. Without strict boundaries in place, an attacker's text input can break out of its intended parameters and rewrite the server's back-end logic on the fly. SQL injection is the exploitation of this exact collision between data and code. It is the process of turning a passive input into an active system command. A successful injection yields immediate results. Attackers can bypass authentication screens entirely or force the database to disclose sensitive, encrypted records. From there, data theft rapidly escalates. Attackers can delete entire tables or exploit system-stored procedures to achieve remote code execution, compromising the host operating system itself. The methods used to achieve this range from direct, visible data extraction, known as in-band attacks, to highly complex blind inference techniques, where the database reveals secrets without ever displaying a single record. This has created an ongoing arms race between attackers crafting obfuscated payloads and network defenders trying to filter them out. As we will see, surface-level network filters are inadequate against these techniques. True defense requires structural shifts in how applications process information. The root of this vulnerability lies in dynamic query construction, the practice of building database commands on the fly by pasting user input directly into a query template. Look at this comparison. A normal query checks the username and password. An injected payload alters the structure. Entering OR1 equals 1 creates a tautology, making the username condition true. Finally, the concluding hyphens instruct the database to ignore the password check entirely. The server discards the password requirement entirely. It reads the true statement from the username field, finds a match, and logs the attacker in. A single unsanitized punctuation mark forces the database to abandon its own security logic and grant administrative access. Attackers rarely deploy these payloads blindly. Their first step is systematically mapping the target, triggering specific errors to identify the database engine and the current privilege levels. This block of server-side code from a vulnerable web page illustrates how developers facilitate these attacks by using user-supplied text to dynamically filter a product list, ignoring secure coding practices. This opens the door for an in-band union attack. The union operator in SQL combines the results of two or more independent select statements into a single output. Here, the executed query shows the attackers splicing a request for the users table into the application's legitimate request for the products table. The database executes both and returns them together. The only requirement for this technique to execute successfully is that the attacker's spliced query must match the exact number and data types of the columns in the original product query. By satisfying that condition, union-based injections transform a harmless, public-facing search bar into a direct pipeline for extracting back-end credentials. Administrators often try to mitigate this by configuring applications to suppress all error messages and database outputs, but this does not stop the extraction. Instead of asking for data directly, attackers use blind or inferential SQL injection. They submit payloads that ask the database true or false questions, observing how the application behaves in response. If standard time delay functions are disabled by administrators, attackers deploy a heavy query. This specific Oracle syntax commands the database to select and cross-join system tables multiple times. Evaluating massive, complex multiple cross-joins requires significant computational power, an action which intentionally spikes the server's processing time. The attacker ties this heavy query to a true or false payload. If the server takes exceptionally long to respond, the attacker knows their injected logic evaluated as true. Application silence does not equal security. Attackers can map and extract entire databases purely by measuring the processing latency of their payloads. This flowchart details the traditional network perimeter. An incoming payload must pass through the web application firewall and intrusion detection system before it ever reaches the web application. Traditional intrusion detection systems rely on signature detection. They scan incoming traffic for known malicious strings, like the standard or 1 equals 1 tautology. Attackers easily bypass these filters by altering the syntax of the payload, changing its appearance without changing its executable logic. One method is string concatenation. By breaking identifiable keywords into smaller pieces, like splitting select into cell and ECT, the payload evades signature verification. Because the IDS signatures only check for exact string matches, the fragmented code passes right through. Once inside, the database's SQL engine simply pieces the instructions back together and executes them. URL encoding provides another layer of obfuscation. By replacing key characters with their hexadecimal ASCII codes, like swapping a single quote for %27, attackers completely mask the malicious command. Because attackers possess near infinite ways to morph payload syntax, network firewalls are structurally incapable of stopping a dedicated SQL injection attack on their own. Effective defense must be built directly into the application's source code. The primary software defense is strict input validation. This ensures that user-supplied data cannot influence the logic of the code. This table compares the two major approaches to validation: blacklisting, which rejects specific bad inputs, and whitelisting, which accepts only known, approved entities. Blacklisting is inherently flawed. It requires developers to anticipate every possible malicious character or encoding variation, which we have seen is easily bypassed. Whitelisting is the industry standard for secure access. It uses regular expressions to define a strict, approved set of characters, rejecting anything outside that predefined range. In application security, assuming all input is hostile until mathematically proven safe is the only reliable baseline. To neutralize the threat entirely, developers must combine proper validation with output encoding and parameterized queries. Parameterization physically separates the user's input from the database's execution logic. It seals the data inside an impenetrable boundary before passing it to the server. This forces the database engine to treat the input strictly as literal data. Even if malicious commands are present, they are neutralized and cannot interact with the surrounding code. Finally, secure architecture requires defense in depth, specifically enforcing the principle of least privilege at the database layer. The web application should only connect to the database using an account with the absolute minimum permissions required. If an anomaly does bypass the application logic, restricting these privileges prevents a full operating system compromise. Surviving SQL injection requires abandoning the hope of perfectly filtering bad traffic. Instead, we must architect systems where malicious data is structurally powerless by design.